Hope you have safe trips back home, and hope none of you have gotten sick. I very much hope that. Yeah, without further ado, let's have Phiala deliver her second lecture on Lattice QCD.
Okay, excellent. So if you remember where we left off yesterday was we had introduced Lattice QCD as basically a way of calculating path integrals for quantum field theory, and in this case for QCD, but you can also do lattice field theory for other types of field theories, numerically on a discrete Euclidean spacetime. So Euclidean, so that we get rid of that oscillatory integrand and have something we can do tractably numerically. Discrete, because the lattice regulator regulates the theory, and also gives us something that we can do numerically. So here's our path integral. Remember, we want to calculate the expectation value of some observable O. Here's our QCD action that has the fermion and the gauge parts. We integrate out the fermions numerically. That gives us this fermion determinant here, exponential of just the gauge part of the action, and our observable, whatever operator we want to compute, which depends now on the gauge fields, U. Remember, we had to put the gauge fields on the links of the lattice in these parallel transporter variables, the U, and on the fermion matrix. And this du here, defined with that lattice regulator, now becomes basically a numerical integration in this very high dimensional space where the dimensions come from the lattice volume. So that's L cubed by T, if we have the same number of sites in each spatial dimension and some number of sites T in the temporal direction, times the spin and color degrees of freedom. So if you multiply that out for typical lattice scales, this becomes a very high dimensional numerical integral in something like 10 to the 9 to 10 to the 12 dimensions. Because it's such a high dimensional integral, the way we do it numerically is by importance sampling, by sampling these gauge field configurations, these U's, with this part already baked in as the probability distribution over those samples. And then we do computations just by evaluating this thing on the U's sampled according to that probability measure. And you take the mean and the standard deviation over those samples to compute your observables essentially. So that's where we left things off. Any questions before we get back into it today? Okay, cool. So the last bit about this formula, which we hadn't properly defined, was this S-glue, so the gauge part of the lattice action. So we'll just go through that very quickly and then talk about observables. So just like with the fermion part of the action, there are choices here in discretization, and all the different choices will have different, the errors will come in different powers of the lattice spacing A. And there are pros and cons to making different choices. But essentially, we know that closed paths of gauge links, so any closed paths of some links around some shape, also known as Wilson loops, can be used to construct all gauge invariant quantities that involve only the gauge fields. So we can certainly write this gauge action just in terms of various closed paths of gauge links, so various Wilson loops. And just as for the fermion action, like I said, the precise construction is pretty much irrelevant if you have the right continuum limit, but some will have better or worse discretizations than others. So we're going to construct the action out of closed paths. Closed paths of gauge links, I should say. So the challenge of writing down a gauge action for lattice field theory then just becomes, how do you write -1/4 f mu nu in terms of some closed paths of gauge links, and to what order in A the lattice spacing is that valid? So the simplest thing we can do is to write it in terms of just the simplest possible loop, the 1x1 plaquette. So that's the simplest closed loop, or the 1x1 plaquette. which is just the product of links in this 1x1 shape. So if this is some site n on our discrete lattice, we can take the link in this direction, the link in this direction, the link in that direction, and the link in that direction to make a closed product of those links, which will give us a gauge invariant object. So we can define our axes here, mu hat directions here. Okay, so this plaquette, we can write that out explicitly. So it's the plaquette at some lattice site n, that's this corner here that we've labeled by n. And we can write that out. We can take the real part of the trace of this link here, u mu, so that's in the mu direction, sitting at site n. So that's this guy sitting at site n, going in the mu direction, that's that way, times u nu, starting at n plus mu hat, that's this link. Then we have this next link, so that's u mu dagger at n plus nu hat. So the dagger is of course making it go backwards that way instead of that way. And the last link, u nu dagger n. Okay, so that's the product of links here. And it's not obvious until you start to Taylor expand it. But if you just Taylor expand the path ordered expression for these u mu's, remember that they look like exponentials of a's, a being our gauge fields, then you can rewrite this in terms of your a mu variables and see how this relates to the field strength tensor. So, and in fact, if we just Taylor expand it, and I won't go through all of that Taylor expanding here, it's a good exercise just because of our lack of time. If you just Taylor expand the u mu's in terms of a mu, we can see that another way of writing this looks like this. Where we can identify that field strength tensor here. So the plaquette ends up looking like 1 minus some constants in terms of the field strength tensor. We were looking for exactly a quarter F mu nu. So we have our F mu nu here. The Taylor expanding in powers of the lattice spacing means that this expression is only, of course, accurate up to some powers of A and some powers of the coupling G. And so just like our fermion actions, in the limit as A goes to 0, we're going to recover what we wanted that action to be in the continuum here. So obviously this is not quite right. We have this 1 minus here, so we can just rearrange. And this gives us what's called the Wilson gauge action, which is sort of the simplest one, that we can write our gauge action like this. As 1 minus the plaquette, which gets rid of this 1 here and gives us just our F mu nu squared part that we wanted. And in the limit as A goes to 0, this looks like what we wanted it to be. Okay, so remembering here, lambda was the set of all the points on our finite lattice. Mu and nu are these Lorentz indices or these direction indices here in the gauge links. And so we can identify the gauge action we wanted with a discretized version in terms of this plaquette. Okay, so just like with the fermions that we didn't go into in too much detail, the same is true here for the gauge action, that you can improve this gauge action. So you can remove some of the leading discretization errors here by adding additional things to it. For example, you can build not just these 1x1 plaquettes, but say rectangle shaped gauge links. And you can Taylor expand this rectangle shaped gauge link, get see what expression you get, and include it with a coefficient that exactly cancels out the leading discretization errors here, for example. And so that's how you get improved actions. They'll have names like the Iwasaki gauge action or the tree level improved gauge action. And all that means is that you've taken this and added a few extra things to it, a few extra loops to cancel out those discretization artifacts. Okay, so it can be improved. Add extra terms to the action to remove leading discretization artifacts. Okay, so now we have the total lattice action. Just looks like the gauge part and the fermion part. And there's some choice for each of these pieces. And those choices will mostly affect, in the fermion case, of course, how well chiral symmetry is respected and how big your discretization artifacts are. Okay, so just before we move on, we can do a quick check-in about symmetries. And so what about the SU3 gauge symmetry that we had? Sorry, was there a question?
No, it was noise from the hallway.
Okay, great. So SU3 gauge symmetry, is it preserved? Is it not preserved? How is that reflected in our lattice action? Okay, so the SU3 gauge symmetry is preserved. We went to, considerable effort to make it so, right? So this is preserved. What about Lorentz symmetry? Yeah, I see some shaking of heads. That's right, that's not preserved. It's broken down to the hypercubic group. Which induces some operator mixing under a normalization that's not there in the continuum. Have to be careful of, to find ways of avoiding that. So typically you choose particular operators in irreducible representations that can't mix with anything else lower dimensional. And so those are then safe things to calculate where you don't have additional power divergent operator mixing. We're not going to go into any great detail here, but I keep saying power divergent operator mixing is something bad. That's of course, if you have an operator mixing that goes like 1 over the lattice spacing, that's not going to go away as you take the lattice spacing to 0. So that type of operator mixing is particularly difficult to deal with in lattice calculations, because as you take this limit, which you have to take, it keeps getting worse. But if you can write down something that does mix, just because it's in a different irreducible representation of the hypercubic group, then you don't have that problem. And then finally, chiral symmetry, which of course depends on the action. All right, so now before we move on to observables, any questions about this? This is sort of just the end of last lecture. Yeah.
When you wrote the QCD action in the first lecture, you included the theta term. Could you briefly comment on the possibility of including that in the lattice action?
Yeah, so I mean, the theta term's built out of the F mu news here. So you can sort of construct it in a similar way to the gauge part of the action. There's been some nice work in the last few years. Any other questions? Okay, cool. So observables. So this is really where we hopefully get a little bit of intuition on what you can actually compute in this framework. So what you can compute are Euclidean endpoint correlation functions. Right, that's basically what I wrote at the very top at the start of this lecture. So you want to relate the physics that you want to do to matrix elements of local or non-local operators in your Euclidean spacetime. And once you have that relation, well, you know how to get to that physics. So can calculate Euclidean endpoint correlation functions. So I need to relate the physics to matrix elements, or of local or non-local operators. Okay, so non-local operators, you'll be hearing about a bit from Michael Engelhardt later today, I think, and you'll see that, you know, this relation, I'll go through some very simple examples, but you can get pretty complex in how this relation is. For example, the physics you get might come out as, you know, some limit in a sequence of different non-local operators as you take the operator extent to infinity. Right, the relation doesn't have to be as simple as the ones that we'll do now, where you can just clearly see how this matrix element is related to that physical matrix element that you're interested in. It could be some, you know, you could calculate some pieces of an effective theory. You could calculate some, yeah, you'll see more this afternoon. Okay, so let's look at probably the simplest example. Let's think about the mass of something, the mass of the pion. And we can calculate that from 2-point correlation functions. Okay, so let's think about a hadron 2-point correlator. And we're going to look at two ways of writing it. Okay, so I'm going to call this C pi for a pion correlation function. And I'm going to break up my, you know, 4 vector X into just the spatial part X with a vector on it and the temporal part T. And at some point I might get lazy and forget to write that arrow on the X, so you can either call it out or fix it for yourself. Okay, so this 2-point correlation function we're going to define here as the expectation value of an operator inserted at xt and the dagger of that operator inserted at 0, 0. And I'll talk more about what these are in just a minute. But essentially, these are just some operators with the quantum numbers of the state that you're trying to create. So in this case, it would be some operator that you construct that has the same quantum numbers as the pion. So let's write this in 2 different ways. So we spent more time talking about the path integral, but let's also write this just in terms of a transfer matrix or a trace in our Hilbert space. So hopefully this will be a familiar sort of expression. Okay, so this is writing this as a trace in Hilbert space, or a transfer matrix, where here the transfer matrix looks like the Hamiltonian, right? Because the Hamiltonian generates translations in time. This operator's here at the position 0, and we've just, this transfer matrix here is going from time 0 to time t, hence the t here. And this one here is going from time t to back around the lattice back to time 0. And so the total temporal extent of the lattice is big T. So that's why this big T is coming in there. Okay, so this is a transfer matrix expression 1, and we can also write this in the path integral form that we've talked more about. So here, writing out our gauge action and our fermion action. So this is path integral. Okay, so, right, and as I said, this operator, O here, which I'm calling O pi, is what we call an interpolating operator. And all it is it has the quantum numbers of the state of interest. Okay, so for a pion, say pi plus, we have a U bar and a D, and we have axial structure. So it's a gamma 5 for our pseudoscale, right? So we can write this as a U bar X, gamma 5, dx, for example. But that is certainly not the only choice, right? Like I said, anything with the right quantum numbers goes. So you could write, for example, here's a different interpolating operator for the pion. We could write it as a U bar, a gamma 4, gamma 5, doesn't change our quantum numbers here, where these Q tildes that I'm writing down is some sort of a smeared quark field where I've just taken some smearing function f, which I'm not going to find exactly what that is. It could be whatever you like, that's going to sort of sum that quark field over some set of neighboring sites and sort of smooth it out. You could do that with some sort of a Gaussian kernel or however you like, right? So any interpolating operator with the quantum numbers of the pion. Okay, so starting from these two different expressions here, 1 and 2, 2 here, when we rearrange that, we'll see how to compute this thing in lattice field theory. And when we rearrange 1, we'll see how to interpret that to pull out the mass of the pion from the thing that we compute. Okay, any questions so far? We're going to rearrange this and then this. So we'll see all these expressions again next. All right, cool. So let's start with our transfer matrix here. So start from 1. Okay, we want to rearrange this to solve for the time dependence. And remember, the time here is our Euclidean time evolution, right? We're going to solve for the time dependence of this correlation function. So C pi xt, we had here our transfer matrix. Okay, this was the same expression we had. So we can rewrite this instead of writing it as that trace. We can put in sort of at the end here a sum over all states in the Hilbert space and write it equivalently like this. Okay, so this is just re-expressing that trace into terms of a sum over all states in the Hilbert space. Okay, and now we have this thing looking again like a matrix element here. We can think about inserting a complete set of states in here, for example. Inserting that complete set of states will give us something useful, right? We will then have this H can act on that state there to pull out the energy of that state. When we insert another complete set of states here, this Hamiltonian will be able to act on those states to pull out those exponentials of the Hamiltonian, to get rid of the operators and get just energies, just numbers back into these expressions. So inserting that complete set of states, let's write it out like this. Now we're summing over 2 complete sets of states, those 2 resolutions of the identity. Oops, that I should not be there, of course. Just a default reaction to write an I in an e to the minus h. Okay. Okay, so all we've done is insert our resolution of the identity twice here. Now we can act with the Hamiltonian here on these states to pull that out and pull those exponentials of energy now out the front of our matrix element expression. I promise we're not going to do too many lines of algebra. Don't want to spend all our time doing manipulations, but I think this is important to see once. So now what we've done is we've brought out the time dependence of this 2-point correlation function. We have here these exponentials with t's in them. There are no more t's over here. These are just some matrix elements. These are just some numbers that depend on the operators, right? So this is, part of the story here. We also have the z here. So we can do exactly the same thing for z, and then we'll simplify this. But let's just think about z. So if we do the same thing, so z we can write in the transfer matrix picture just in the same way, and we can do exactly the same manipulation, right? This Hamiltonian can act on that state. It can pull out e to the minus e p t. Which, if we think about what's happening there, that's e to the minus e0t for the ground state, and then a series of smaller and smaller exponential contributions. Right, so we can write that also just as this series of exponentials. That's the 1 over z here, where I've written the difference between the ground state, so E0, and the next energy in our tower of all of the energies with these quantum numbers like this. So E0 is the vacuum energy. Okay, so far we've done essentially nothing. We've just inserted the resolution of the identity twice into this to pull out the time dependencies explicitly, both here and here in the denominator. We can do exactly the same thing. Now, we can, in the limit as this big T, which remember is the temporal extent of our lattice, in the limit as that becomes large, you can see a few things happen. So here, for example, all of these additional terms get damped out exponentially, right? We're taking this capital T large. So these all get small. So this ends up looking like just e to the minus e naught t. Similarly here, when we have a rho here being not the ground state, then E rho is larger than it is for the ground state rho. And so that's then a smaller contribution. And so all of the higher excited states become exponentially damped. And so on the limit, as this time extent of the lattice becomes large, everything gets damped out and we end up with just the ground state here. So taking T large, only rho equals 0 contributes, or you could say it's the dominant contribution. And so what this looks like is this. Okay, so you can already see why I said several times last time that often the lattice volumes will be L cubed by T. So the spatial dimensions will be the same, but then the temporal extent will be different, often larger. And you can see why, because taking this capital T, this temporal extent to be large, is important for damping out a lot of the contributions to this matrix element that we don't care about, right? Okay, so if we now, let's say we're only interested in states which have 0-3 momentum, just for convenience, we can do a Fourier projection. So do the Fourier transform from X to momentum here. So that just looks like a sum over all positions X will give us the 0-3 momentum contribution. Okay, and so then what we're left with is just something with a time dependence. This is our Euclidean time. So just that one parameter, it's the sum over all x's of this guy. And what that looks like, just this expression here, but just rewriting it, it looks like some number times an exponential in that Euclidean time. Well, it's a sum over these exponentials in Euclidean time. So these z's are just these matrix elements here. Those are just some numbers that depend on the interpolating operator we used. So this 2-point correlation function, it depends on the energies here of all of the states for which this thing, which is these overlaps of the operator onto that state, are not zero. So that is, it depends on all of the energies of the states that can be created from the vacuum by this creation operator. In general, any creation operator is going to create a state that's a linear combination of all of the possible eigenstates of the Hamiltonian that have the same quantum numbers as that state. So if this is for the Pion, then you're not just going to create the Pion. You'll create excitations of the Pion. You'll create 3 pions in the j equals 0 state, and so on. And so that is the tower of states that will contribute to this sum here. And obviously above the ground state, all of those contributions are exponentially damped by the fact that they have larger masses or larger energies in their exponential contribution here. Of course, you could potentially write down an operator that's just completely orthogonal to some particular state so that this matrix element vanishes and it has no overlap onto that state. And if that happens to be the state you're looking for, that's bad, and you wouldn't necessarily know that that's happened. It's also really unlikely to write down something that's just perfectly orthogonal to some particular state, right? So in general, you think you've got the entire tower of things with the same quantum numbers. Okay, are we clear so far on this expression for a 2-point correlation function? I see something in the, I can't quite see the chat. Maybe someone can read it out.
It says from Gabriel, it says, how are quark field operators and the interpolating operators defined in terms of the fields in the path integral? Is it just the same asymptotic Fock state expansion as in perturbation theory?
Yeah, I mean, so that's essentially what we've done here, right? In this transfer matrix picture. And then here in the path integral, those will just look like, when we come to the next expression, those will just look like the fields in the path integral. And here, yeah, you're right. That's essentially what this picture is doing. Okay, cool. So this expression, I mean, it doesn't tell us how to calculate anything, but it tells us that once we've calculated this, we'll know if we construct this function, we have just a function depending on one variable, that's the Euclidean time, and this is the dependence it will have. So if what you're looking for is the mass of the pion, you need to pull out this from that functional dependence. Okay, so starting from 2, that's the path integral expression, we can see how to compute this thing. So let's just remind ourselves of that path integral expression. So here I'm writing out the interpolating operators explicitly. Okay, so we have our U and our D quark fields here. We have our gamma 5s sitting in here. This just looks like a path integral. So the first step, remember, was to integrate out the fermion fields. So that's going to do 2 things here. It's going to, well, it's going to get rid of the fermion fields here because we're doing the integral, but it's going to bring determinants of M down. So what determinants of M should we get in this case? Is there one term with a determinant? Are there multiple? Any guesses?
Is there one for each flavor?
Yep, thank you. There'll be a determinant for MU, and there'll be a determinant for MD, because we're going to do a two flavor calculation here with up and down quarks. Okay, we have e to the minus s glue. And the other thing that integrating out that determinant does explicitly is it gets rid of these quark fields here. We've integrated them out, right? And we're left with quark propagators, which look like inverse M's. So we'll have here two quark propagators. We'll have the U quark propagator, which we get from these guys. So it's going to be a U quark propagator going from X to 0. And we'll have a D quark propagator from those guys going from 0 to X. So this thing, after integrating out the fermions, looks like a U quark propagator from X to 0, a gamma 5, a D quark propagator from 0 to X, and a gamma 5. Okay, so quark propagators. Which you have to compute by inverting M, which is this big matrix, right? So we see already two computational costs here. There's the sampling over the gauge fields, where we have to make these high dimensional configurations with the right probability distribution, with this probability distribution. And then on each of those gauge fields, we have to compute this thing, which, as you can see, involves inverting really big matrices. So there's the cost of getting the gauge fields, then there's the cost of doing the calculation on the gauge fields. Okay, so then how we actually compute this in Lattice QCD is, of course, that we're going to sample n config, so some number of gauge field samples, and compute this trace on each sample. So this is our ensemble of gauge fields. And then we need to sum over positions to get C pi t. Okay, so then what we've done is we've computed C pi t numerically by doing this. So remember, sampling all the gauge fields, computing this on each gauge field, and then averaging. And then we need to take this and fit it to this functional form to pull out the thing we want, which is the mass of just the lowest state in that sum, the mass of the pion. So compute C pi t numerically, then fit to the functional form, which is this thing, to determine the mass we want. Okay, so let's just be a little bit concrete about that. So I'm about to scroll this thing off the page, but I'll write it down again in a second. So let's be concrete. So remember, C pi t looks like this sum over exponential. So we have some number times e to the minus m naught t, where that m naught is what we want, plus some other number, plus a more damped exponential, because m1 is larger than m naught here. And it's just a sum over multi-exponential sum. So what we will typically do is create what's called an effective mass function, which is defined like this. Which is just the log of the ratio of this thing at different times, right? And taking the log of the ratio of this thing at different times, it's obviously going to pull out that m0 constant plus some correction. So this looks like m0 plus some exponentially suppressed contribution. So that's just some constant, which, of course, depends on these z's here. You can solve for what that is. And this is the energy gap to the next state. So that's always positive, that gap, because we have the ground state here, m0 is the lightest mass. So obviously the value in forming this function is that it gives us the constant plus something exponentially damped. So if we see what that looks like, effective mass plots look like this, where you'll have some so this is m0, this is t, this is the effective mass. So what you'll see is that you have some exponential contamination from excited states. It's called excited state contamination, right? That's from this damped exponential and everything else in the series that we've neglected. And then this effective mass function will plateau to what will be your ground state mass or energy m0. So typically you compute this thing with bootstrap or jackknife resampling to get estimates of the errors. And then this growth of noise here of the error bars is exponential with t, which we'll come back to more later if we have time. So errors computed with bootstrap or jackknife resampling, growth of noise, exponential in t, which we'll come back to. Okay, so then we're pretty much there, right? I mean, there's obviously different ways of going from this, which is what your raw lattice data will look like, to an estimate for m0. Simple way is you find the region where this looks sort of flat, and you compute the average of all of the points in that plateau region, right? And that will be an estimate for this value m0. More sophisticated ways are to fit multi-exponential functional forms, just using something like a chi-squared minimization. You have to be careful because all of these points are very correlated. They were all computed on the same configurations on the same ensemble, right? So you have to make sure to get your covariance matrices right and so on. But this then just becomes a fitting problem. You know the functional form, you have the data, get out the parameter you want. Okay, so get m0 by fitting to the multi-exponential functional form. Okay, one other thing worth mentioning is if you, instead of doing the naive thing of fitting just the plateau, if you fit the multi-exponential functional form, of course, you'll also get these parameters, right? You'll get out some constant here, but you'll also be able to get out this energy gap. So that's one way you could try to get out not just the ground state, but the excited states. But it's pretty hard. And obviously it's pretty hard numerically because all of the excited states are exponentially suppressed. So you won't get very clean signals. So a more typical way is to take a whole set of interpolating operators with the same quantum numbers. So maybe different smearings, maybe for the Pion, you have not just the one with gamma 5, but the one with gamma 4, gamma 5, and so on, and make a whole n by n matrix of correlators. And what each of those correlation functions will give you is something with the same energies, but with different overlap factors. Because remember, the overlap factors depended here, they were these things, they depended on that interpolating operator. So if you have then a system of equations with all of the same energies, but different coefficients here, you can then solve that system with something like solve the eigenvalue problem, solve a generalized eigenvalue problem to try to get out the excited states as well. So that's typically how you'd access excited states. It's just obviously expensive because instead of one correlator or a couple, you need an entire matrix of them. Okay, any questions about this? All right, so that's for the mass of the pion, but it's pretty much the same story no matter what you want to calculate. So I know Michael will be doing TMDs. Let's do something that's sort of one step closer to that, but not quite there, which is matrix elements of local operators. So let's think about just GA, axial charge. Okay, so if we want to calculate GA, so the isovector axial coupling of the nucleon that's defined by a matrix element, we can write down its definition. Okay, so let's write down nucleon states at some momentum. That's these n's. We're going to put in our axial current here, our isovector axial current. And this is just our definition of GA, right? And on this right-hand side here, we have some spinors. Oops, gamma mu. So spinors, these are nucleon states. This thing here, okay, we can call this just our axial current, J3 mu 5, where the 3 is, of course, because of the tau 3. What space is tau acting in? Yeah, so tau is our Pauli matrix in our flavor space, if you like. So that's like 1, 0, 0, minus 1. That looks like U minus D, right? So hence the iso vector axial coupling of the nucleon. Okay, so that's defining GA. So if we want to compute GA, we need to relate this matrix element to something like a 2- and 3-point functions that we can compute in Lattice QCD. And then once we can identify this matrix element, so this current between nucleon states, then we can get out GA. So we can see how to do that, relating it to a 3-point function. Okay, so let's write down our 3-point function here. Now, I'm now going to have 2 times in here, and we'll see where they come from in just a second. So I'm going to have our nucleon operators, and I'm going to insert also our axial current. Okay, so this looks a lot like our 2-point function. We have here our nucleon operator, our creation operator, and here our annihilation operator. In the middle, we've inserted the axial current. Each one of these guys is coming with his own position. So we've got 0, Y, and X. we're summing over X and Y, which is just projecting to zero momentum. It's projecting the whole thing to zero momentum at the sink, or where things are being annihilated, and also at the operator insertion. So that's the sum here, and the T and the tau correspond here, the tau to the position, the time position we're inserting this current, and T to the final time position here. So again, the transfer matrix is taking us from 0 to tau, hence the tau, then from tau to T, hence the tau minus T, and then from T back around the ends of the lattice. So capital T is the finite extent, so capital T minus little t. Okay, so the nucleon operator here, obviously that's going to be just something with the right quantum numbers for the nucleon now. So, you know, that would look like, it would have a U, it will have a D, it'll have a U, and then it will have, you know, the right color and spin indices. So here the color indices are the ABC, this thing here is a spin index. Right, so something like that, just with the right quantum numbers for the state you're interested in. Okay, so how are we going to get from here to something where we can identify this matrix element? Okay, we're going to do exactly the same trick we did before, right? We're going to first write this trace as a sum over all states. In the limit, as big T goes to infinity, we're going to have just the 0 state dominating again, exactly like we had before. And we're going to insert sets of complete states here and here, so we can pull out all of those exponentials with the Hamiltonian. So I'm going to do all of those steps sort of together, insert 2 complete sets of states and take the limit as big T goes to infinity. And we now have this. So this was just inserting 1 complete set of states here, 1 here. Now we have something where we can again act with the Hamiltonian to pull out energies. These things here, these overlaps of the operator onto some state, I'm just going to call that some constant again, some Z. We don't really care what that is, it's just a constant we have to fit. So we have some constants, we have some energies, and now we have 2 different times sitting in here. We have T and tau, which are, if you like, the sink time and the operator insertion time. And then we have a matrix element. Okay, so this is now almost this, right? The only difference is if we want to calculate this matrix element in the ground state of the nucleon, then we want both N and M to be the lowest states in that tower of all possible states with the right quantum numbers, right? And once we've got this thing here with N and M being the lowest states, then we've been able to calculate GA. So fitting this, you can already tell that there's a lot of free parameters if we just calculate this and try to fit things, right? There's these Zs, those are constants. We can't fit those at the same time as fitting this thing, which is also a constant. And there are the energies in here. So rather than trying to fit all of the free parameters just to this one expression, we can get some of these free parameters from a different correlation function. Any guesses?
Two-point function.
Exactly. The Zs will be the same overlap factors, these things that we saw in the 2-point function example. So are the energies. So we can compute those from a 2-point function, then put them into our fit for the 3-point function to isolate this. Or alternatively, something that's very commonly done is ratios of 3-point functions to 2-point functions are taken that will eliminate the leading time dependence. Can be very convenient. But essentially, you have some functions with some free parameters, combine them to eliminate anything that you can that you don't want to fit. It's sort of just a question of what's the most efficient thing to do calculationally or computationally at that point. So use 2-point function with the same operators to determine Zn, En, or often useful to form ratios of 3-point and 2-point, or 3-point and 3-point, or 3-point, 3-point and 2-point. You get the idea, to eliminate whatever you can eliminate before trying to do the fits. Okay, so that's what the time dependence looks like. You've still got to do the other half. You've still got to compute it. And as we saw up here for the 2-point function example, right, the actual computation here, this is just tying together an up quark propagator and a down quark propagator in this trace with the appropriate gamma 5s thrown in. It's going to be exactly the same thing with the 3-point function. And the easiest way of knowing what to compute is to do it using a skeleton diagram, like just to draw it. So compute the 3-point function in terms of quark propagators. And you draw them typically using something like a skeleton diagram. So in this case, if you work out all of the different contractions you need to make, we will see this, that we have, this is X, this is 0, this is Y, this is U, D, minus X, 0, Y, this is again a J mu, and U, D. Okay, so when you go to write everything in terms of these quark propagators, these M inverses that we had to get by inverting the Dirac matrix, you'll see that you'll get several terms in that expression. These lines with U on them represent a U quark propagator, so M inverse U, and similarly the lines with D here, M inverse D, and how they're put together here is telling us about that trace, and the J mu is representing where you have that current insertion either on the up quark line or on the down quark line. So this is just an illustration of the different contractions you get if you go through the maths. Okay, and so then that's it. You need to, again, you calculate the gauge fields, you compute propagators on them by inverting the Dirac matrix on each gauge field. You tie them together by taking gamma matrices and traces of these propagators. Then you average that thing over all of your different configurations, all of your different samples, and then you have something that you need to fit to some functional form to extract the part that you're interested in, the specific matrix element, the particular mass, and so on. Okay, any questions here?
Question.
Yeah.
Go back to where you were defining the effective mass for a second.
Yeah.
So it looks like you have to expand in small in the small d, the small time difference. Is that correct? And that's where you're saying the source of uncertainty primarily comes from. Why you're saying it comes from time? Is that correct?
So time is discretized, right? So D here is just an integer of the number of discrete time steps you're taking. Most commonly, this will just be 1. So remember, so C pi as a function of t is just a number at each one of your discrete time steps that you have across your lattice.
Oh, okay.
So most commonly, so you just have this list of, say, like 20 numbers, and you're going to take the ratio of that with the list shifted by 1 or by 2 or by 3.
I see. So how, if we don't know M0, or if we don't know the mass of the pion, how do we know that the next terms in the series are really starting to become negligible? Does that mean we have some a priori knowledge about those higher mass states?
Yeah, so what you know is that they are higher mass, right? So that's why getting to the ground state of the system is the easiest thing to do, because that will always be the dominant term. If you have states that are really close together, this will still be exponentially damped, but not much. And then you'll have a really tough fitting problem on your hands. So that's why, that's one of the reasons why nuclear physics gets hard. When all of the states get really close together, this damping doesn't damp so well.
So when you do the fit, it would work well and say, oh, I guess the states are closer than I expected.
Yeah, so you'd have, a lot more contamination to the point where, this exponential could be coming down and be really like blowing up before you get to a plateau region. So then you need to really trust your multi-exponential fits, or you need to do that other thing I mentioned where you do multiple different correlation functions, which will all have different overlaps onto the excited states from the different interpolating operators. And then you'll have a system that you can try to solve to eliminate that contamination.
I see, that makes sense, thank you.
Yeah, no worries. Anything else?
I have a question.
Yeah.
In Lattice papers, when they provide observables in terms of different values of the quark masses, is that what the 3-point and then subtracting off the 2-point function, is that what that is?
Sorry, could someone closer to the mic repeat that maybe?
Or can you move the mic?
Yeah, I can move it. Hold on.
So, can you hear me?
Yeah, that's better, thanks.
Yeah, okay. So in Lattice papers, when observables are provided in terms of different values of the quark masses, is that subtracting off the common z's from the 2-point functions? Is that what's happening there?
No, so this entire process is done for one fixed set of parameters. Like you choose your quark masses, you choose your volume, you choose your coupling, and then you do this whole thing and you get out this M. But then you can do the whole thing again for a different set of quark masses. And so then what you'll get is you would have done everything, the fits, everything, gotten out your M, but then you'll get that out for different sets of quark masses, and you can plot basically your, M0 versus, the pion mass. And so you get the final answer, which came from here, from some fit band here, and that will be 1 point on this plot.
Okay.
From some set of quark masses, and then you'll do different, and then you'll fit to that and try to get to M pi as 140 if you had to do it at a larger than physical value of quark masses.
Okay.
Could I add maybe something about Andrew's question? You were looking at that logarithm of that ratio of correlation functions. All you're doing here is if you take that apart into the logarithm of the numerator minus the logarithm of the denominator, all you're doing here is taking a finite difference approximation of the derivatives. Right, you have e to the minus energy t. You take a logarithm, now it's energy t, and now you take a finite difference. Now you've got the energy. So that's all that's happening here. You're taking a discretized derivative. That's all.
Okay, I took that difference and I was like, oh, I feel like I have to expand something now.
No, there's no expansion. It's just d is 1. That's the smallest increment you can take. So it's your finite difference approximation of that derivative. That's all.
Perfect, thank you.
Okay, any other questions? Okay, cool. So what kind of correlation functions are calculated? So I'll put a few notes when I post a pretty version of these later. But so 2-point functions, obviously we saw an example for spectroscopy. And we talked about how you can get not just ground states, but excited states. 3-point functions, you can take matrix elements of local operators like we did here in this GA example. So get things like GA, nucleon electromagnetic form factors, moments of Pion distributions you can write in terms of matrix elements of local operators. B pi decay form factors to constrain CKM matrix elements. All those sorts of things you get from 3-point functions, just like this example. 3-point functions, you could take matrix elements of non-local operators, which I think you'll hear more about today, to get things like quasi and pseudo PDFs and TMDs. And you can go bigger, you can go 4-point functions, which get useful in double beta decay or KK bar mass difference calculations and so on, right? And the whole thing just comes back to identifying that correlation function with the physical thing that you're trying to calculate, like some matrix element. Okay, so sort of to summarize where we're at, workflow of lattice calculation. Okay, so one, we generate this set of field configurations. So this is by Hamiltonian or hybrid Monte Carlo, like we talked about last time. And these are your important sampled field configurations. And just for an idea of scale, this takes a lot of computing. So let's say 100,000 cores or thousands of GPUs, right? These are sort of large scale computational tasks. Then on that set of configurations, and so this set of configurations, this is for, you know, fixed quark masses, fixed coupling, fixed lattice geometry, right? This whole process happens for fixed ensemble. Then you compute propagators. And of course, the determinant of the fermion matrix and taking the inverses for the propagators are expensive. So typically you use iterative methods like conjugate gradient, things like that. And we might talk a little bit more about that later if we have time. These are sort of smaller scale, right? You need maybe a few hundreds of GPUs, but you need to do many of these propagators per configuration typically. So this is the next, you know, big computational task. And since the ensemble of gauge fields can be reused for multiple different calculations of different observables, this is often one of the big costs in a lattice calculation, is computing all the propagators you need. Then there's contraction. So you need to contract all of those propagators into correlation functions. So this is, you know, let's say a few GPUs, but if you start doing things like nuclear physics calculations, the number of contractions can grow factorially. So even though that looks small for each contraction, that can also grow to be a significant computational cost. But typically the propagators are the big cost, other than the generation of the field configurations. Then there's fits and analysis. This is the sort of thing that you might do on a local cluster. And then this whole thing, right, you repeat. For different parameters. So that's, you know, different, let's say, couplings, different quark masses, different lattice volumes, and so on. And then you need to extrapolate. Okay. Oh, my writing seems to have deteriorated. Sorry, I'll try to slow down a bit so it's a bit more legible. Okay, any questions here? Okay, great. So let's think about a few things. Let's think about, so this is the last part, let's think about uncertainties, and then let's think about what's easy and what's hard. So uncertainties. What uncertainties do we have? Anyone want to shout some out?
Statistical uncertainties.
Thank you. So those go down like 1 over the square root of the number of measurements you take. Okay, what other uncertainties are we going to have? What about in the fitting that we have to do to the correlation functions? Anything there? Okay, so there's the systematics in those fits, right? You've got, what fit range, what fit form. Do you do this thing of just fitting the plateaus? Do you do a multi-exponential fit? What do you do if you get different answers? How do you estimate a systematic uncertainty from your choices there? Then we have, we've got the finite lattice spacing. We've got to take the lattice volume to infinity. So these are, typically you'll do calculations on several ensembles, or hopefully, maybe not for sort of proof of principle work. And you extrapolate. Then of course, you might have a pion mass that's different from the pion mass in nature. And as we'll get into in just a second, light pion masses are expensive. So especially if you're doing something really hard and really expensive for the first time, you might have the wrong pion mass. And so that would be a systematic in your calculation. You might have, okay, I'll call it charge symmetry violation, but light quark masses might be different. You probably might not have QED included in your calculations, or maybe you do. Maybe you're doing lattice QCD plus QED, but maybe that's dropped. You might have chiral symmetry not well respected by your action, and so on. And so these are all things that might be neglected, but might be important for high precision. Then you might need to include them. So there's really, depending on what you're trying to do, some of these effects, maybe you can't neglect at all. Maybe they come in at few percent precision and you're trying to get something at few percent precision. Maybe you're trying to get something at 20% precision and you can completely ignore these because they'll be swamped out by your statistical uncertainties and everything else becomes irrelevant. Right, so this is sort of a calculation by calculation question. So then what is hard? Or expensive? So light quark masses are hard or expensive. We've sort of seen why already. Does anyone want to guess? So remember, we get the quark propagators by inverting the Dirac matrix. So why might that get hard for light masses?
Small eigenvalues are hard numerically.
Yeah, so but basically that Dirac matrix that you have to invert gets closer to being singular, right? And so that's a numerically tough problem. So computing propagators gets hard. So there are nice algorithms to deal with this. So things like adaptive multigrid instead of conjugate gradient that make that a bit better, but it's still a hard thing. There's something else. So you need bigger box sizes when you have light quark masses. Any guesses why? bigger box sizes relative to the size of your finite volume effects from having a finite box size.
If the particle can tell it's in a finite volume, is that what you're saying?
Yeah, basically. So the finite volume effects are set by the longest correlation length, right? Which, you know, so a lighter particle has a longer correlation length. And so then the finite volume effects get bigger when your quark mass gets lighter for a fixed volume. So typically you want to go to larger volumes. So since the finite volume effects set by longest correlation length. So the pion mass. Okay, so light quark masses get hard. That's why you'll sometimes see, extrapolations down to the physical mass instead of calculations right at the physical mass. Large lattice volumes are hard. So this one's sort of obvious, but any suggestion why?
More sites to calculate?
Yeah, right. You just have a large number of degrees of freedom. I mean, also the Dirac operator has more low modes, but basically it's just you got a lot of degrees of freedom for each configuration propagator, so it just gets computationally expensive. Fine lattice spacings. So I guess it's not escaping anyone that all the limits we want to take, like the lattice volume getting big and the lattice spacing getting small, are hard. So fine lattice spacings. One easy way of thinking about this is that the hybrid Monte Carlo algorithm that you use to generate the gauge fields we discussed yesterday, it's really an updating algorithm, and those updates are basically close to local, or they're diffusive. So that means that if you need to change physics on some fixed physical scale corresponding to something like the size of your proton, something like that, as the lattice spacing gets small, the number of these close to local updates you need to change physics on that scale diverges. So if it's very coarse, maybe you only need a few updates for that scale. If it's very fine, you need a lot of updates for that scale. So this is a manifestation of critical slowing down in this context, but basically it just means that ensemble generation gets harder and more expensive as A goes to 0.
Can I ask a question?
So I'll try to sum. Yeah, go for it.
So when you say that's diffusive, so at some point, at least you know when you're done because everything sort of stops diffusing?
No, so you want to think about that algorithm more as you're going to make a small change to each configuration in a long chain. And in the end, you want lots of these configurations in the chain, right? So you're not going to evolve for some time and then you're done, right? You're using this as a stepping through configuration space in a way that, because of the detailed balance and ergodicity of your algorithm, will give you that the equilibrium distribution of that whole chain has the right probability distribution. So by diffusive, maybe that word was confusing. I really meant more that the updates only really decorrelating the configuration on a short distance scale in each step. So if you like, another way of thinking about it is that, so it's basically integrating a Hamiltonian dynamics trajectory, but because numerical integration is not perfect, you can only really do that for a quite short time before the numerical integration is bad, and you'd have to have a low accept rate when you fix up that non-perfect integration with an accept reject step. So you're limited to these really quite short integration trajectories, which means that you're not really changing the configuration that much from one step to the next, is what I'm trying to get at there. Does that make sense?
Yeah, more so, thank you.
No problem. So more steps needed to update physics at the scale of the relevant correlation length. As the lattice spacing goes small. Okay, then large Euclidean times. So So these things, right, are all sort of things that you set before doing your calculation. You fix the coupling, which fix the lattice spacing, you fix your lattice volume, you fix the quark masses. And so changing those parameters can be, can make your calculations more expensive. But also when you're doing your calculation, remember we had the effective mass as a function of Euclidean time, and I said that the uncertainties grow exponentially. So large Euclidean times is get noisy. And so I'm going to try to sketch an argument for that. So of course we want to go to large Euclidean times because that's what damps the excited states. But it gets noisy. So Euclidean time evolution dampens excited states. But the signal to noise degrades with T. So let's sketch what happens here. So we can think about the 2-point function for the proton. And this is just a sketch. I'm not going to be careful about all the sums, etc. So we're going to have 3 quarks at some position X, 3 anti-quarks at some other position 0 here. When we integrate out the fermions, we saw a picture of this in terms of these 3 contractions, right? That's what our 2-point correlation function for the proton looked like. And we saw that this will look like, as time goes to infinity, this will look like some constant times e to the minus the nucleon mass times that Euclidean time. So that's sort of the scaling of the signal of that 2-point correlation function. If we think about the variance, so this is thinking about the noise part, we can write the variance as, right, this is the familiar form. Then we can think about the correlator corresponding to this part here of the variance. So that will look something like this. We've got our QQQ. We've got our Q bar, Q bar, Q bar. We've got another QQQ at 0 and another Q bar, Q bar, Q bar. Right, so because we have the squared in here inside that expectation value, right? So we have these 4 sets of 3 quarks. So when we integrate out the quarks, what this looks like is really 6 quark lines here. Note that the QX isn't going to contract with the Q bar Y because the quarks are integrated out before this mod squared thing happens. So we have our 6 quarks here, and 6 quarks propagating doesn't just look like nucleons propagating an n plus n bar, but 6 quarks you can also rearrange into 3 sets of 2 quarks, which looks like 3 pions. So remember when we were talking about interpolating operators and correlation function, you get the whole set, the whole tower of all of the states with the right quantum numbers, and they all contribute. It's a similar thing here, that this noise correlator, or this variance correlator that tells us the scaling of the noise, is going to look like not just e to the minus 2 mnt, but also something else that you can make with that combination of quarks. That's e to the minus 3 m pi t. And because 3 times the pion mass is less than twice the nucleon mass, it's actually this term that's dominant here. So if we want to think about the signal to noise, it's going to look like, our correlator over the square root of this variance, which is going to look like, to first order, an exponential of mn minus 3 halves m pi t. So the signal to noise is obviously going to get worse and worse as t gets larger. So that's why I drew those error bars getting bigger and bigger. That's why if you can design an interpolating operator to have little excited state contamination, so you can fit at earlier Euclidean times, you get higher precision answers, right? Because if you have to fit at late Euclidean times, the noise blows up. Okay. Any questions about that sketch or about any of the things we've talked about so far? There's a few more things I want to mention before we finish up. Okay, great. So excited states are also expensive. I mean, they're damped out by Euclidean time evolution, like we saw. So the variational method, which is this one where you form a matrix of correlators and solve the generalized eigenvalue problem, that's also expensive. You need a whole matrix of correlators. So excited states are in general harder than ground states. It's because they're damped out. Okay, then or also another way of saying that is you could say that you really want interpolating operators which have good overlap onto those excited states and lower overlap, so that these the Z factors, which look like how strongly the interpolating operator overlaps onto a given state, should be large for the excited states and small for the ground states, and that might be harder and less intuitive to construct for states high in the spectrum, where we have less intuition about what they look like. Okay, large momenta also get hard. So anything at large boosts gets hard, which is particularly important thinking about some of these quasi and pseudo PDF and TMD approaches. So the argument's pretty much the same as the signal to noise approach argument that we just made. But if we have non-zero hadron momenta, let's think about the signal is going to look like e to the minus EPT, where that's now the energy at some given momenta, that's the EP there. But in the variance, the quark and anti-quark have opposite momenta. And P plus minus P equals 0, right? So the variance is still the same. So the variance still looks like this E minus 3 M pi T as the leading term. And so then the signal to noise looks like e to the minus EP minus 3 halves M pi T. So it gets worse with increasing P. You also have a more dense excited state spectrum, which adds to all those difficulties that we talked about before of dampening out the excited states. Okay, so like quark masses, large volumes, small lattice spacings, large Euclidean times, excited states, large momenta, they all make things harder. Nuclei, I'm going to give just a quick mention to. If you want to do, not just a proton, but some sort of a nuclear state with more quarks, you have the same signal to noise issues like you do for large momenta here, but you also have a factorial growth in the number of contractions you need for a given atomic number, because you just have that many more quarks that you have to pair up in all possible ways that are consistent. And so that can also make the contraction part expensive, and that factorial grows really fast. Even writing down all of the contractions gets really hard or impossible quickly. A's atomic number here. Okay, so we're pretty much out of time. So the last thing I wanted to do was sort of give you an idea of typical scales, which is obviously very specific to this point in time, and these things can change. But I think it's important to have an idea if you come across a lattice calculation in the wild, is it a very coarse lattice spacing or is it very fine by the current standards? So I'm going to say that lattice spacings, and there are other lattice people in the room who might have objections or contributions that are very welcome. But I'm going to say typical lattice spacings at the moment are somewhere around 0.04 to 0.12 Fermi. So of course, now I'm putting this in physical units, which also gives you some sense of how lattice spacing compares to like some physical scale, like the size of a proton, which are coming with lattice volumes of, so that's L cubed by T, let's say 24 cubed by 48 is reasonably small these days. 128 cubed by 256 is a pretty big size. Obviously some are smaller, some are bigger, but that's about a typical range. What that will mean is if we think about this, so 128 cubed by 256, if we then go times 4 directions times NC squared, so times 9 times 2 for the real and imaginary parts, that gives you about 4 times 10 to the 10. So when I was saying somewhere between 10 to the 9 to 10 to the 12 degrees of freedom, that's how you get to something of that scale from some of these numbers here. And 10 to the 4 times 10 to the 10, that's something like 320 gigabytes per gauge field configuration. So they can get pretty big. Okay, number of configs can vary really widely depending on what you're doing. So let's say 100 to 100,000. Probably this is quite high on that high end. Number of measurements, which means how many different times you might do several measurements on a configuration by taking different quark propagators on the same configuration and assembling it into a measurement of your observable. Again, this will be hundreds to, hundreds of thousands. Quark masses, which we normally think of in terms of the pion mass that results. So 140 MeV is of course physical, and so there's lots of calculations there now. But for some things where physical masses are too hard, there's heavier masses used, up to maybe 800 MeV pion masses, and also sometimes there's lighter masses used for thermodynamics and places where you might have a reason to go to lighter masses. Number of flavors. So we talked about this a bit yesterday, but you might have a 0 flavor calculation, a quench calculation. You might just have 2 flavor up and down, 2 plus 1. So this notation here with the 2 plus 1, of course, 2 plus 1 is 3, but this means that those 2 quarks have the same mass and this one has a different mass. So 2 plus 1 or 3. So either 3 mass degenerate quarks or 2 light, 1 slightly heavier for the strange, or you might see 2 plus 1 plus 1, 2 plus 1 plus 1 plus 1, and so on. And computing resources, let's say small calculations would be a few million core hours, and state of the art or really large scale for established calculations that we know how to do and are trying to get precision down. These would be multi-year, hundreds of million core hours on sort of national scale facilities. Okay, so the other thing I'll put in my notes when I post them is some references, good places to read more about Lattice QCD, but that's all I wanted to cover.
Okay, thank you, Phiala. Last chance for questions.
I actually have a bit of an odd one. So actually, I'm in the process of reviewing rewriting research presentation, research paper on Lattice QCD. That's for my chance exam at my university.
I was wondering if I could cite your talk in it, because you've actually explained this process a lot more succinctly and a lot more in depth than the textbook I'm looking through right now.
Sure.
Thank you.
As long as you cite the organizers.
I'll tell you how to cite it.
Well, anyone else here or on Zoom?
I have probably a naive question. With the signal to noise ratio, it seems to be a consequence of us going to Euclidean time and it just being this damping function. If we stayed in regular time, I'm sure that there's a cost lurking somewhere, but if we stayed in regular time, I mean, it seems like you'd be able to predict which data points would still be really, really good because maybe the signal to noise would be oscillatory. But if I could say this point's going to be good, this point's going to be good, and I could throw out the other data points, is that not something you can do? Would that not work?
Yeah. Well, so there's a few things coming in here. So this Euclidean time, it's not real time, right? You're not evolving the system in time. It's sort of your fictitious additional time dimension whose entire usefulness is this thing where you can damp out the excited states. If we hadn't gone to Euclidean time at the start, we would have had that oscillatory integrand. And if you think about, trying to numerically integrate something like a sine function, it's really, really hard. It's essentially a sine problem, right? You get contributions on both sides of zero that have to cancel out to give you the answer, which is something small relative to those contributions, right? So that's just, if we hadn't done that Wick rotation, you get a numerically very complicated problem. But the sort of the other part your question was getting at is on, time evolution, actually thinking about, the real time evolution of a system. And I mean, that's one of the reasons people are so excited about potentially doing lattice field theory on quantum computers and things like that. And also some tensor network approaches, other ways of trying to not have to do this transition, which makes real-time evolution really hard to get to.
Yeah, I always get confused. I understand the importance of going to Euclidean time, but I imagine at some point you want to transform back, but I don't know when you would do that. I figured if we're already here, could we transform back to regular time? Or when are you allowed to do that?
So that matching really happens after you've got that matrix element, right? So what you do, when I said you need to figure out what matrix element is going to get you the physics you want, the matching to what you actually want in Minkowski space is part of that translation into how do I go from this matrix element that I want and relate it to something that I can calculate in my Euclidean lattice calculation. And so there might be a few steps involved in that matching, not least how your momenta are defined in Minkowski versus Euclidean. You have to make sure you match up the right way, and all the signs on your gamma matrices. You can get additional eyes in places that you have to match up right.
Maybe I can add something.
Speak over here.
Well, so the thing we usually do is when we calculate 3-point functions, we put the operator of which we're evaluating the matrix element, we put it at one time. And so if you put it at one time, then there's no issue of translating a Euclidean time dependence to a Minkowski time dependence. You're doing everything and call it time zero, and time zero is the same in Euclidean and Minkowski, and there's no analytic anything to do. It's just that's the number. If you really wanted to convert an actual Euclidean time dependence that you're getting here into a Minkowski time dependence, you would have to know the poles that you go over when you try to analytically continue from the Minkowski axis, from the Euclidean axis to the Minkowski axis, and you have no idea what those are. So in general, you just don't have enough information from your Euclidean time dependence in order to reconstruct the Minkowski time dependence.
Okay. I see. Thank you.
Okay, well, thank you very much.
Can I ask
Phiala,
one more
for-
question?
well,
I think it's quick,
okay, go.
very quick. When you look at the lattice volumes, where that talk up?
That's not true.
Oh,
You need
well, when you have a lattice volumes, you put 128 cubed by something cubed. Are those representing actual sites, or are those, I should divide that by the a spacing a for the number of actual sites?
No, so those were for sites. So those were in terms of lattice sites, 128 sites in a spatial dimension, and that example was 256 in the time direction.
Basically, you have like a billion sites that you're working on for the big calculations.
Yeah, but then the other degrees of freedom that you need to take into account are also the, spin and so on. So
That's just
yeah,
pure that big a number to keep track of.
exactly.
Thank you.
No problem.
All right, now we'll thank Phiala.
Thank you very much. Bye-bye.
Thanks for those beautiful lectures.